Okay, hello everyone. Welcome to the next in the series of TVS Colloquia. It is my pleasure to introduce today's speaker, Ashley Villar. She is a Simmons Junior Fellow at Columbia University, and starting this July, she will continue her research as an assistant professor at Pennsylvania State University. Ashley mostly works on data-driven methods and machine learning techniques to study eruptions, mergers, and explosions of stars. Her very special interest is in understanding the physics of optical transients through multiband light curves. She became involved with Rubin in 2018 and is a member of TVS Science Collaboration, where she works mostly on representation learning and classification of extragalactic transients. And the latter is also what Ashley will talk about today. So please, Ashley, the floor is yours.
Okay. Yeah, thanks so much. Oh, I'm unmuted, right? Excellent. Okay. Yeah, thank you so much for organizing this. So yeah, I'm going to talk about exactly what was described. So how we're doing classification and anomaly detection in multiband light curves in preparation for LSST. The first part of the talk will be very generic overview in case people aren't also working on extragalactic transients. But I feel like it's a fun audience in that many of you are my direct kind of peers in this. And so I also at the end want to get into kind of the nitty-gritty details of how I'm approaching and thinking about these problems, especially because if you want to collaborate, I would love to apply these techniques to different types of specific scientific domains. And please interrupt me throughout if you have any questions. And the other last thing is please ignore any sounds in the background, like my dog barking or right now shaking. Yeah. Okay. So very broadly, I'm thinking about time domain astrophysics, as I'm sure everyone here, transients and variable stars. And what I really enjoy about this field is that it's such a wide range of astrophysics available. And I'm stealing this really beautiful plot from the Villar collaboration, which really shows you the hierarchical structure of the physics we're trying to understand. There are many classes within classes within classes of different physics. And what we want to do is untangle those physics. Largely, I think about the left side of this diagram, which I call the kind of eruptions, explosions, and collisions of stars. These are transient or kind of terminal, non-repeating events, which include most famously kind of supernovae, but also galactic things like novae. And that's really what I'm going to talk about is how do we understand the classes and the physics within this realm. So what is there? There's also a zoo in even this little hub of the larger diagram. This is a smattering of the different physics we can expect through pretty pictures. So for example, I'm thinking about things like the beautiful Eta Car eruptions, finding those in nearby massive stars and really learning about the late stages of massive star evolution. Thinking about things like type 1a cosmology, which I'm representing as these candles, and using those as a standardized candle to understand the expansion of the universe. Newcomers to the field are the mergers of binary neutron stars and potentially neutron star black hole pairs that produce electromagnetic radiation, which we call a kilonova, which is telling us about not only the fun gravitational astrophysics of these events, but also binary evolution and the nucleosynthetic evolution of our cosmos for the heavy elements. And then down here, I think I saw Subi in the audience and she would like this. So also the tearing apart of stars that wander too close to supermassive black holes, so known as tidal disruption events, which really teach us about the properties of those black holes. So there's a whole zoo. And the key point is broadly, these are falling into different classes of different astrophysics. And the goal is to take the zoo of observational properties that we see and map them onto this zoo of astrophysics and understand really what's happening for not just a given interesting event that tells us really directly about high energy physics, but also full populations of events, which tells us about underlying progenitor systems. It really is a zoo in this header, and it's a confusing little branch diagram that's telling you specifically for supernovae the different way that we classify them using spectra. So largely the way this works right now is that we take a spectrum near peak when it's at its brightest, and we look for the presence or absence of certain atomic lines. And then from there, we can kind of subdivide it into phenomenological categories. These categories, though, really do map onto the astrophysics. It corresponds to, so if I see hydrogen, I know that that massive star has retained its envelope. Or if I see, if I see UV excess, then I know that that has something to do with some additional shock physics happening. So probably an interaction from a previous burp of a star is happening. So they're really intimately connected, but right now our class system is based on getting a spectrum and seeing what type of class it looks most similar to. This is hard to do. It's expensive to get a spectrum, but it's cheap to get light curves. I will argue, and I think most people agree, that a lot of this physics is still encoded in the broadband optical light curves, which are kind of like a very low resolution form of the spectrum. But the timescales, the colors, the brightness of these things also encode the underlying physics. And so that's kind of a key point, is we believe that we can use just the light curves to do photometric classification into this zoo of spectroscopic classification categories. Okay, the reality of the situation is that they're not beautiful light curves. They're kind of, I don't want to say terrible, but they're not wonderful. They're often pretty sparsely sampled, not sparsely, but not great sampling relative to the duration that these events will last for. They're also irregularly sampled, both in time and in the different filter, which is represented by color here. And they are, by their nature, aperiodic. So it can be kind of hard to hand engineer features or properties of the light curves that you want to use for classification. And that's one of the fun problems in this field, is that we really want to be able to pick the most information-rich features of these light curves to do our classification, because we're trying to classify based on spectroscopic labels that rely on a lot more information. So I would argue that actually pretty simple features capture a lot of the underlying physics. So this is a very famous kind of phase space made famous by Monsi Kozliwal, which is duration luminosity. So if I just look at different supernovae, I keep track of how bright they got in a given filter and how long they lasted by some metric. And I make a contour plot of that, like I'm showing here. Then I can get these these loci of points that I'm showing as the regions for different classes. So here I'm showing the most vanilla supernovae, which are really just powered by radioactive nickel decay. And for a very reasonable range of physical parameters that we can really expect in the universe for these classes, this is kind of where we expect the vanilla supernovae to lie on this feature space diagram. And what's fun is that it's actually pretty narrow if you include all of the other engines and progenitor types that we know about. And so this is what this like ridiculous plot is now showing, is a survey of those different underlying engines and systems and physics that we expect, and their realistic parameter ranges. So now you can see, okay, this is where the vanilla guys are. But if I see something that is, for example, very bright, but rising and dimming very rapidly, it's, for example, very likely a relativistic event like the afterglow of a GRB. And so even these very simple features actually end up being really useful for at least somehow tagging the underlying physics. Small point that this feature space, so this was a theoretical study I did that didn't really think about rates. So the reality is that this is not a uniformly populated type of feature space, which makes the problem more complicated. So one added kind of Z dimension here is the intrinsic rate. Some things are much more rare than others. And then the other thing is your bias of these, of the surveys we're thinking about, which are flux limited, untargeted surveys. And those are really biased towards long lasting bright things, which makes sense. Okay, so the state of things. So right now we're discovering something like 10,000 supernovae every year. And so I'm showing here a histogram that's just tracking the history of this, which I think is kind of fun. So the number of supernovae on a log plot over as a function of time. And what's cool is that it's been growing exponentially pretty much for the last 20 years. And this has really been driven by the rise of untargeted surveys. So things like Pan-STARRS, PTF, ZTF have really contributed to boosting up this number in recent years. Everyone knows about the survey. So in now at this point, so in October of 2023 is my understanding, there's going to be this wonderful new survey that I'm not going to tell you all about because you know all about it. But what's really, I'm going to tell you why it's so exciting for the field of transients in particular. It's going to just blow us out of the water with the number of discoveries we should have. So this arrow is representing LSST. LSST is going to actually break the exponential growth, and we're going to discover something like 1 million new supernovae and other extragalactic transients every single year. So this is a 2 order of magnitude increase. And this, to me, is really going to propel us into this era of big data where we really need to be thinking about, oh boy, how do we solve this classification problem and other associated problems for this data set? And I want to highlight that at the same time, this black line is representing the number of supernovae with spectroscopic classification that we can expect. Very loosely, we don't really expect our spectroscopic resources to more than like double once in the time before LSST comes online. So I've represented it as a horizontal line. So I don't remember. Yes. Okay. So unfortunately, this means for us, so right now we have spectroscopic identifications between 1 and 10% of supernovae, more like 10%. And this is going to drop to something like 0.1% of all supernovae discovered in LSST. So we need to really be getting strongly away from spectroscopic classification. It's just becoming something we can't rely on without heavy filtering of the data stream for interesting candidates. And as a final motivation, so a different way of looking at this is not only are we going to only be able to spectroscopically identify thousands, if we're being generous, of supernovae, but then realistically on top of that, we need to devote human hours to researching this, or a different way of saying it is we need to also devote multi-wavelength follow-up campaigns in real time to some of these transients. I would very optimistically say maybe 100 or so can be followed per year with additional, I don't know, like 1 additional observation. That's very tiny. That's 1 in 10,000. So that's equivalent to saying, if we discover 10,000, in 2020, what if the entire supernova community had to pick 1 object to write a paper about? That's the level of importance that we need to decide upon as a community for follow-up information. So I really consider these purple guys to be the needles in the LSST haystack, the things that we really need to follow up in real time. And I will argue later in the talk, I think not on the next slide, later in the talk, that I think it's not unrealistic to be, and I think a lot of people in this room agree, it's not unrealistic to be looking for new or unpredicted astrophysics, and we'll be looking for anomalous events as a large part of that data stream. Okay. But in general, so now we're going to get nitty gritty, and I definitely welcome questions. So in general, classification is just a first step for any time domain studies you want to do, whether that be real-time follow-up or population statistics. We have to have some sort of identifying, I think this is the underlying physics flag on events. And so that's what I'm going to talk about. And specifically, my way of doing this is thinking about machine learning. And in particular, I think about representation learning, which just means I think about ways of learning a model without telling it what the model is. We have very nice models for supernovae, like SALT 3 just came out, which is awesome. But what if we maybe don't know what we want to pick? And that's the idea. Very small aside, because I think it's important actually, is that for machine learning, because you're not relying on model physics necessarily, the data that you're using is so important in training a data-driven model. And so I want to talk quickly about two data sets that I think about a lot. The first is a real data set, as in it's real data, and that's the Pan-STARRS Medium Deep Survey. So this was a survey conducted by Pan-STARRS, so 2010 to 2014. It was, yeah. So in this survey, it found about 5,000 supernova-like transients, where that just means they seem to rise and decay, like a normal supernova would. About 500, so 10% of these were spectroscopically classified and had host measurements associated with them or directly from the supernova itself. There's also a dedicated campaign to get some more host measurements for about 3,000 of them. What I really like about the Pan-STARRS Medium Deep Survey is, so we've published this set of supernova-like transients very recently, myself along with Griffin Hosenzade. What I like about it is that it's very similar to LSST in filters, cadence, and depth compared to something like ZTF. So it's a really nice training ground if you care about specifically classifying subclasses of supernovae like I do. And then the other data set that I really like is, and I think this crowd's familiar with this one too, is Plastic, which is this really wonderful community survey led by Rick Kessler, Renee Holchek, Gautam Narayan, I'm sure other people. It's just awesome. It's an effort by community to figure out, hey, what are all the different transients and variable stars that we can expect to see in LSST, or ones that are just kind of out there and we maybe won't see. Let's put it in a survey, let's put it in a simulation of 3 years of LSST data. And then they actually gave it to the Kaggle community, so this online competition community, to say, can you classify as many events as you can? Comically, the winner was Kyle Boone, an astronomer. So apparently our domain expertise is very important in this problem. But it's really wonderful because because real data sets are working in the thousands of supernovae, and this simulation is working in the millions of supernovae. And so if you really want to be studying these big data techniques, this is like the simulation to be using. And I will use both in this talk. It won't matter a ton. Okay, so first I want to talk about classification. And the way we're going to do this is it'll be with the Pan-STARRS, so real data set. And it's going to use a semi-supervised method using something called a recurrent neuron-based autoencoder, which is a lot of words, but I'm going to explain what everything means and why we actually chose to go down this route. First, I'm going to, on this slide, just say what semi-supervised means, because I'm getting more and more into unsupervised learning. So supervised learning just means that I'm going to show a machine examples of some data and then what the data is called. So type 1A light curve, and I'm going to tell it this is a type 1A light curve. And I show it lots of examples. Unsupervised means I am going to just show a machine learning model, lots of examples. I'm not going to tell it what it is. I'm just going to show it lots of examples, and it's going to learn something about the underlying data structures or models that are used to build those examples. Semi-supervised is a mix of the two. Sometimes I'm going to show it some labels, sometimes I won't. And I'll explain when I do and don't. This autoencoder I'll explain in the next few slides, in this slide apparently. So an autoencoder is a way of building a model without telling my computer any physics. So the way that this works, and the reason why I'm doing this is because I want to eventually use different features of my light curves to do classification, but I don't want to pick the features by hand because I might not be picking the best ones, or there's a chance that my computer will pick non-linear, more interesting features. So the way autoencoders work are you show a neural network, which is just a series of matrix multiplications where you can tune the elements of the matrix and then some nonlinear functions. I show it lots of examples of multi-band light curves, like I'm representing here, that are encoded as just vectors. And then I say, okay, machine learning model, return those exact light curves back to me. And you might say that's very silly. Obviously, that's easy to do. Just multiply those vectors by 1 and you have them back. But the trick is that these light curves contain hundreds of data points. But my matrices get smaller and smaller until I have to squeeze the most important information out of it. And that happens in this bottleneck layer that's called an encoding layer. And so in my case, I have a single vector that has to represent the full light curve in just 10 numbers. That's about the same number of free parameters that we have in analytical light curve models. And this is to me very analogous to learning a light curve model. So if I were to do a physical model, I would say this light curve is being driven by some ejecta mass, some energy, etc. In this case, I'm saying I don't know what those are, but hey, I'm going to give you 10 free parameters to fit this light curve, and that's what it's learning. The second thing about the autoencoder that I use in particular is that it has something called recurrent neurons. And that just means that instead of taking a static image of a light curve, it's going to actually feed every single observation into it so that I can update that encoding or the model for the light curve. And so the way it works is that I show it a few data points, it gets an encoding, it gets the model. But then I show it more data points that says, oh man, I wasn't doing that right. And it updates for a better encoding. And this happens again and again as you get more data points. And for people who know machine, what's nice about this is that it allows for uneven data sets, which is extremely useful in LSST, where we know we have uneven heterogeneous data sets. Okay, so I show this example of in pictures how this actually works. So this is real data from pan stars, GRIZ, which are being represented as these points. And this I know is a spectroscopically identified type 1a. These lines are the decoded model from my autoencoder. So these lines represent the model that the machine learning algorithm has learned, and I haven't told it about underlying physics. I will say that I'm not saying this in detail, but the architecture has a fun structure designed so that we can actually interpolate and extrapolate light curves, which is unique amongst architectures. Okay, so I say that this is totally machine learned. You can tell because it's kind of bad. So with about one high signal noise data point, it's doing terribly. It's kind of a dim and short-lived transient. It doesn't quite know what to do. So it's maybe not the best encoding. But what's fun is that just a few days later, and still arguably pre-peak, it actually pretty quickly picks up on the fact that, oh, this probably reaches about the correct magnitude for a type 1a. It's still not quite there. And I'll show you the next slide. This is really what we're waiting for, is now once it's right after peak, the encoding's really great. And it's picking up on second order kind of features of type 1as, in particular, this double peak in the redder bands, the Z band. So it's learned something about the underlying physics once it sees a full light curve, and it can get a better and better idea of what the underlying physics probably looks like by showing it more data. So now the idea is that we're going to use this model, those kind of 10 numbers, to classify the light curves. Sorry. So we did that for the Pan-STARRS medium deep survey. And like I said, about 3,000 of these had spectroscopic redshift estimates. And so we did this using absolute magnitude. So we relied on those redshift estimates. So we photometrically classified these pan-STARRS supernovae. And this is kind of the breakdown of the classes we found compared to ZTF, the bright transient survey. It's pretty similar, which gives us some hope that we're doing it correctly, especially if we correct for kind of our known biases in the model. This is, I think the crowd, I'll explain. So this is a confusion matrix that's showing how well we're doing. It just compares the truth against what your neural net or your methodology is saying. And you want this diagonal to be a nice dark blue, which means that you're getting most of them correct. you can see that we're not quite getting most of them correct, but we have a good idea of why we're doing poorly in some places. So really the ones with very few examples in our data set, and I'm talking like dozens of examples, really aren't being classified well. So we really think that with more labeled examples, we can actually properly identify these. Sorry, my dog's growling. I don't know if you can hear him. They're intruders, apparently. Okay. What's also fun is that with this study, so Griffin Hosenthal had a sister paper where we both applied totally independent photometric classification methods to the same data set. And so it was kind of one of these first situations where we could ask, what do you do when you have different uncertain classification probabilities and you don't quite know if they're real because they're from these machine learning methods? And so we're starting now to build this kind of new framework for what is I'm calling like probabilistic or messy classification, and see how often do you expect to agree, and is that agreement actually helping you in having true labels? Let's see where I am. Okay, so I want to step back and say that this seems like a complex method, but I would argue that all the decisions were made for realistic reasons. So we used a semi-supervised method where the unsupervised part was learning the encoded kind of parameter space. The supervised was then training a classifier. This was helpful because we could use the full data set instead of just using the spectroscopically identified subsample. We can really use the full kind of knowledge that exists. The autoencoder is useful. It extracts unique and, like I said, nonlinear features that may or may not be helpful in classification. In this case, they were. It performed somewhat better than having hand-tuned engineered features for a specific problem. The recurrent neurons, they were very important because we have live updating light curves once LSC comes online. So we really want something that can update its prediction. Then the last thing, which I didn't talk about, let's see, I will talk about pretty quickly, I think, is that this method can actually be used to look for the needles. And I will explain quickly how this works. So now I'm switching to a different project that was just pretty recently on arXiv. It's in review right now, so I definitely welcome feedback. It uses a really similar architecture. So we're going back to this autoencoder. I'm going to learn some representation of the light curve, so 10 numbers. But I'm going to use this representation instead of for classification to look for weirdos. And here's how I do that. I'm kind of lying in that there's been an update to this. There's been a small update to this architecture. Instead of learning one vector, I'm going to learn a distribution of vectors. And by that, I just mean I'm learning two vectors. I'm learning one that represents the mean of a multivariate Gaussian and one that represents the diagonal of the covariance matrix. And then whenever I want to ask my autoencoder, hey, can you show me what you think this light curve based on these vector values looks like? Instead of picking the mean value every time, I'm going to pick one vector example from that multivariate Gaussian. And from that, I get like a collection of light curves. This is really useful because it helps smooth out, how do I say this in an easy way? It helps to smooth out this kind of learned vector space, and it makes it continuous so that you can actually, this is easier actually, so that they look nice in this space. The space looks like a Gaussian. That's very helpful for picking out outliers versus having lots of little islands of points. And so what we're going to do now is we're going to look at this learned latent space, which means we're going to take this little bottleneck encoding vector. And here I'm just picking two of those. And for every single supernova, now this is in the plastic data set, I'm going to plot what it looks like. And you can see that most of them cluster nicely, but some of them look super weird. They are out of distribution anomalies. And we want to know, are these anomalies interesting? And can this be used as an anomaly finder, or are they boring? So that's what we did. And specifically, we didn't just look by eye for these. We used an algorithm. We used something very easy called an isolation forest. It's one line in Python. And the way that it works is very intuitive to me. It just says, that I think that I'm going to try my best to isolate different example. Oh, I guess you can't see my pointer. Can you see my pointer?
We can see it.
You can see it. Oh, great. Okay. So I am going to try to, as best I can, isolate different examples of this distribution using horizontal or vertical lines, so just planes in the space. And so, for example, if I want to isolate these two guys, I just put a line here. And the idea is that if I take many, many different cuts to isolate you, I probably look pretty normal. But if I take one cut to isolate you, I probably look like a weirdo. And that's exactly what happens, is that it uses a series of decision trees to divide the data set again and again. And your anomaly score is inversely related to how long it took me to isolate you from everyone else. And so in this way, I can actually rank every single transient in plastic and hopefully in LSST to look for the weirdest ones. So we do this. And what's great about plastic is we know the underlying physics, so we can color code what these numbers mean. It's a very hard plot to follow, so please don't follow it. It's showing you the cumulative distribution function for the various classes in plastic. Please don't try to cross-correlate these. I'll just tell you what you should gain. It turns out that the very common classes, like type 1As, which is this orange guy, in general have lower anomaly scores. They look more normal. The weirdos, which are the ones that are just much, which are the true minority classes in plastic, there are fewer of them due to volumetric rates and biases of the survey, typically have much higher anomaly scores. They skew towards the high end. So that looks good. It looks like that our algorithm does in fact pick up on weirdos in the set. So I'm going to zoom in. The second question though is, can I pick out those weirdos early enough to do something about them? I argued in the beginning that the needles are only important to me in active follow-up and human hours in real time. So we need to be able to actually pick these guys out early enough to do something about them. So we'll zoom into one example and see if this happens. This is obviously a good example I've chosen. So this is a type of supernova that was modeled, which is called a superluminous type 1 supernova. It's in the minority class because there's like 2% representation in the sample. Physically, it's also pretty cool. We think that these, so like the name suggests, they're really bright. And we think that they're bright because there's extra energy injection from a newly born magnetar with a neutron star with a high magnetic field and a high spin. Okay. So there's something in chat, but I don't know what it is. So this is the light curve that comes from plastic. And then what I'm plotting here are the encoded features, so that vector, over time. And you can see, and they're scaled in a way so they kind of show you that they do kind of converge onto a final encoding. And then the color is showing you when the light curve encoding and going through that isolation forest, when the anomaly score reaches the top 1 percentile. And that happens about a month before peak. And so what's exciting about that is that if you believe this algorithm, then we could trigger the telescope really early and get nice follow-up before peak, which is when you want to do spectroscopic to kind of minimize your telescope usage, but also to try to see early physics that happened before peak. So things like these kind of pre-peak, everything's transient, but transient bumps in superluminous supernovae that we don't quite know the origin of yet. And this last one's showing you visually what's happening in the autoencoder's mind. And what's happening is that now every black point here represents one supernova encoding from plastic, and the purple guy is all this example. And the darker purple represents later in time. So you can kind of imagine him walking away from the distribution. And that's why this is being picked up as now being an anomaly. This is a really confusing plot, and I apologize for that. This is also the last slide. So again, the question is, are we picking these things up early enough to follow? And are we picking up things that are even interesting? And the paper goes into a lot more detail of ways of cutting up the sample, but I would argue, yes, in general, we are picking up on the right things and we're doing it early. And so this is showing you on the left-hand side, how is the anomaly score changing as a function of time as a vector plot? And so here, the interpretation of this plot is that anomaly scores typically are totally stagnant after peak. They're not kind of going all around. It really does converge onto some solution. Now on the right-hand side, I'm showing you kind of true and false anomaly positives. So blue represents, ignore light versus dark. Blue represents something that was classified as an anomaly by the algorithm that is in fact from a minority class, like a superluminous supernova. So that's a good thing. And what's fun is that we typically do flag these as anomalous before peak. So now the orange things are false positives. They're things that we called anomalous, but it's like a type 1A that happens to have a bad photo Z estimate or something. And what's cool is that we typically classify them after peak. And realistically, we probably won't actually trigger those in real LSST times because we've probably missed out on a lot of the physics. So this is good news. So I would argue this algorithm does in fact choose the right things. It chooses them early as well. And it gives you a ranked list. So you can decide yourself which ones you think are important. Okay, I'll end there and just say that I think there's a ton of room for new methodologies in this field. I'm super excited to collaborate with anyone who's interested in this. That's it. Thanks so much.
Thank you, Ashley. So we have a lot of time for questions, and there was a question from Federica in the chat. So,
hi, Fed.
Federica, if you want to.
Hello, how are you?
Good.
Hi, awesome talk as always. Thank you, Ashley. So the question is about the isolation forest.
Yeah.
The isolation forest is trained on the data that you have, right? So it's a model that you train and then you run it and you get a new data point. And so the way I cannot get convinced that you would identify as an anomaly a new anomaly, something that doesn't belong to the anomalous space that you have already seen, because it learns the partitions between the space based on objects that you have identified as anomaly in your training set. So can you convince me otherwise?
That's a very good question. Can I convince you otherwise? I'm not sure. Because I don't remember if I'm lying or not, if I tell you how I did it. So I think I trained the isolation forest on, so the autoencoder and I think the isolation forest were trained on 1% of the plastic sample. So it is actually a very small but representative subset of it. So it has not, I think, learned the larger space and is still able to do this. That being said, though, I think the test of like F-bots, for example, so these, the fast bright transients, which Fed definitely knows what they are, have not been put into plastic in the version I used. And I haven't tested if like that would be flagged as anomalous enough to be something that we would catch. It probably would have a high anomaly score, but it needs to have a really high anomaly score for us in this algorithm to catch it. So I think that's a great question.
Thank you.
Yeah.
I'm still not convinced, but maybe we can work about.
I think that's very fair. Yeah.
Do we have any other questions? So just out of curiosity for me, I'm not that familiar with machine learning, so this is all very interesting. But if you have for your training sample, for example, okay, you take some light curves of different transients, but then you have a transient observed that has some peculiar features, like, I don't know, some bumps or something. How do you, so how does your classifier work then?
Yeah. So I will say we didn't, so like I said, we didn't do the explicit test of what if I design a weirdo and put it in and see what happens. Instead, we just asked more like, what is in the top 1%? What kind of supernovae fall under there? And in general, in the class of weirdos, I don't want to say that. In general, in the class of things that I know are in the minority classes, whether their scores like. Okay, so all of this is to say that It really depends. The algorithm is sensitive to variable sources. So it's very good at finding AGN, for example. So if there is something that really differs from a type 1A like supernova, it seems to be able to identify those. Yeah, but Fed is right in that it's been trained on a subset of of realistic data.
Yeah. Okay, thank you. Any other questions you might have? Yeah, Anu, go ahead, please.
Yeah, I had a question kind of related to whether you can, have you thought about incorporating like, the host galaxy like colors or bumpiness or, like properties of the things apart from just light curves and how
Totally. Yeah, absolutely. So this is something I'm thinking about right now. So there's so many things to say. So I think there's so many ways you can improve upon this. One is hand engineered features like bumpiness. Like I know I can measure variability and I can just give it as one of the encoding space layers. But then things exactly like you're saying, the context of these things also matters. So I didn't do this because in the plastic simulation, that largely wasn't included. It was in some classes, but not in other classes. I believe in the newer version of plastic, there will be a better form of this, which I'm super excited about. And then kind of in real data sets, yeah, I think you absolutely need to include information about the neighborhood of the transient. And one of the big problems to me is having, again, kind of being able to extract features from what I called wide data sets. So things like an image versus a light curve has very different information content, and you want to weight those appropriately. You don't want to be biased by a prior on one. And so I think it's a big emerging field into how to do that properly. Yeah, but I think it has a ton of potential, and absolutely people are already thinking about this too. Yeah.
Could I ask a question?
Sure, go ahead.
So it wasn't clear to me how you defined anomaly. Suppose I'm interested in calcium-2 rich supernovae, and I want to study them as quickly as possible. How would you apply your system to someone such as myself who is interested in a particular type of object? And
yeah, that's a really good question. So on the first question, I should have included a plot on how I did this. We defined minority versus majority classes just by a cut of how abundant they were in the plastic data set. So our minority classes were something like 2% or less, and majority were something like, I forget now, like 10% plus or something like this. So that is how we checked our answer of whether or not we were finding the true minority classes. Now, if you wanted to look specifically for what I call carts, which no one else does, the calcium-rich transients, if you know the physics you have in mind, don't use this algorithm. You can use this algorithm as an input feature to a classifier. So maybe on average, carts have kind of high anomaly scores, but that by itself is not going to tell you that it is a cart. So you're going to want to use a classifier that has been trained on the various subsets of physics that you're interested in.
So given all of the different classifications that you have there, could you assign in time a probability for each one of those that clearly changes with time? So someone's interested in another, TDEs and these calcium. So small likelihood of being the right object, but in time the certainty or uncertainty increases. That is, the probability decreases. So how could you actually apply that in that way?
Yeah, so absolutely. So that's what kind of this first half of my talk was about, was using this as a classification method, where exactly what you said, the probability updates in real time. Every time you get a new observation, the representation of that light curve will update and in theory get better and better. So you get more and more confident, you would hope, in your classification. So in practice, you as a user would use a broker system like Antares or Alerce, where a algorithm like this is plugged into the back end. And you just have to say, I want to find things that are very likely to be calcium-rich transients. And
Right.
those alerts will come to you and the probabilities will update. Yeah.
Okay, well, clearly it's very important that something like this be established for LSST. Yeah.
Yeah, and I would say there's a ton of work that I not really
And
part of
color
that.
should be a very important parameter.
Yeah, definitely. I think Fed is the expert on this, really overseeing the TVS.
Just trying to make sure that we get colors. I don't know that I'm expert, but a lot of pressure to get colors.
No,
Yeah.
well, it's very important. I mean, the data is there and it may be uncertain, but I think it is a very important parameter.
Yeah, I think there's
But-
so many layers to this. Go ahead.
So
Fed.
the thing that Ashley, I think, was referring to is that it's important to get color, but it's important to, especially if you're interested in rapid transients, which I think calcium-rich transients
Yeah, they
also
are.
kind of fit that. So you really need color, like you really need 2 observations in 2 filters at a short distance in time, because the evolution otherwise gets in the way. So I think the problem with Rubin LSST data with color is going to be understanding what is color and what is evolution, because we are not.
So how is color determined? That is every 3 days or 4 days, or are you only using one particular filter?
No, there will be more than one filter, but yeah, but you know, the cadence is not fully finalized yet. So this would be a really good time to voice your opinion about getting multiple filters within a short period of time to actually get color and not like a revolution. It's been decided.
Okay, that I will do.
Yeah. I will also say, so for this specific method I'm talking about, color is, it's not something we measure, it's something built into the model. So every time we get a new data point, the algorithm actually knows, hey, this is the time relative to maximum that I think we're at, and this is the filter color that we have. And so it's learning an evolution of multiple, it's learning the evolution of an SED with time. It's not learning one color or something. Yeah.
Thank you.
Okay, do we have any other questions here? Okay, I don't see any hands up. So I would like to thank you again, Ashley, for this very, very, very interesting talk. And also thanks everyone who joined today. And I hope to see you next month for our next colloquium. Bye.
Okay. Thanks. Bye.